Here you can see not very clear word simulation. I mean, it can have many meanings. I won't be able to give all the details, not enough time, but I hope to explain what I mean by simulation. But mainly, I would like to give the details of my motivation. Then maybe some basic facts and applications. So, all of you are well acquainted more or less with the basics of harmonic analysis. Real harmonic analysis, Fourier transforms. Every textbook or chapter in the textbook gives more or less the same manner. Basics of L1 theory, L2 theory, LP theory, so on. But there is a meaning of the Fourier-Stieltjes transform, or just the Fourier transform of a measure. This is a widely used notion. Try to find the theory, what is given mainly, is a sort of L1 theory. Try to find L2 theory or LP theory. I failed to find any trace of this. So one of my motivations was just a curiosity. What happens with measures in this situation? But I have a more concrete motivation. I give you a partial, not the whole problem, a partial problem, the easiest part of the problem, and will show you where we face a need in some additional tools. We consider the cosine Fourier transform of a function of bounded variation on half-axis, locally absolutely continuous, vanishing in infinity. And you wish to know about the behavior of this Fourier transform. One of the assumptions is that the derivative, and the derivative does exist almost everywhere. A function of bounded variation has a derivative almost everywhere, which is L1 integrable. And we assume that in addition, the derivative belongs to the Hardy class, real Hardy space. Let me omit many details. Just we consider the Hilbert transform. This is the usual Hilbert transform, just reduced to the half-axis, applied to odd function, or extended to the other half-axis in odd way, and understood in the principal value sense. And if the Hilbert transform is integrable, we say that we have a real Hardy space, in this case, reduced subspace of only odd functions. So, the cosine Fourier transform we started with is integrable, and the norm of the L1 norm of the Fourier transform is controlled by, dominated by H1 norm of the derivative. We will use the sign trying to avoid explicit constants. By the way, in the case of cosine Fourier transform, this fact is just integration by parts and application of the so-called Hardy inequality. This is the proof is very easy. A natural question is whether we can get rid of absolute continuity. The first step in each proof is integration by parts. But we can integrate by parts without assuming absolute continuity. We can integrate by parts in the CTS sense and arrive to this integral. Without details, let us assume that we do some actions like before and try to arrive to the case where the Hilbert transform of the measure, and this is also a well-known notion, Hilbert transform, is integrable. To get an analog of what we... And we fail. It is a known fact that if the Hilbert transform of a measure is integrable, then the measure is absolutely continuous. The thing we try to remove comes by force. So what to do? What to do? It is clear that we cannot stay in the scope of Hardy spaces. But there is a scale of subspaces of a real Hardy space, very convenient, useful with many applications, with this norm when P is between 1 and infinity, and in this case, in the case of infinity. This is just in addition to the integrability of the function, its monotone measurand must be integral. And we have these embeddings, and all these are subspaces of real Hardy space and L1. And from these embeddings, we immediately get an analog of the previous results for narrow classes. We can control the Fourier transform. But meantime, we see this result as a consequence of the previous result for Hardy spaces and embeddings. But we know that we cannot have Hardy space framework for measures. But there is a direct proof of this result without using Hardy spaces and Hardy inequality, these strong tools. But this direct proof inevitably uses the Hausdorff-Young inequality. And here is the point where we meet the need to have some additional harmonic analysis for measures. We must have an analog of Hausdorff-Young inequality, at least this. So, it was written, I didn't say that it is a joint work with Laura De Carli, and we decided not to solve this particular problem. To give a general overview, a general approach to all these things, moreover, not in dimension one, but in several dimensions, I'll show you just main notions. The approach is based on associate norms. These are standard things. LP class, the Fourier transform for Schwarz functions. So, when P is between 1 and 2, there are no problems, big problems. The usual machinery can work or applied more or less easily. But when P is greater than 2, it is well known that the Fourier transform can be understood in general only in distributional sense. There are counterexamples that do not allow to any of usual approaches. And we give the following definition. We define the space LP, this head, in the following way. Class of functions which are the Fourier transform of LP prime conjugate exponential LP prime functions. Then the norm is the usual way, and then we consider measures, and from measures we introduce a sort of analog for LP norms. We denote it as LP star. We take this associated norm on functions in LP prime hat. And we introduce these spaces, and we show that this gives us many good properties, more or less similar to those in usual case, and we don't assume the measures to be positive. They can be even complex measures, complex valued, and I'll return to this norm, to this notion when we finish the story with the solution of that problem. There are examples, for example, how the standard Lebesgue measure appears here, only in M infinity. Then what about the delta function? And what is important, we have a Hölder type inequality. You see, it looks it looks more like Young's inequality for convolutions. And indeed, if we assume R to be 1, then we get a direct analog of Hölder inequality. But you see everywhere the norms are newly introduced norms. But we have a more extended, more general case for this. Then different properties. We have no time to consider the duality. Just what we have and what we need, you see that we really need this. We have an analog of the Hausdorff-Young inequality. And what is interesting that the proof uses the standard version of Hausdorff-Young inequality, playing with these norms and these passages. We use standard. We consider the Fourier Stieltjes transform of measures with here is this Hausdorff-Young inequality for measures. We use this norm, otherwise we cannot. And to get a flavor of all this, this classical example, which were classical direction, which was started by famous paper by Wiener and Windner. How the Fourier transform of a singular measure generated by a singular function behaves. The main point here is the Riemann-Lebesgue lemma. For functions, the Fourier transform vanishes at infinity, for L1 functions. For measures, it is not the case in general. The Fourier transform of a measure is bounded continuous function, but not always vanishing at infinity. But here was an example of such a function, and they showed that this delta, for this delta, 2 1/2 is the border. It cannot jump over, so no L2 theory can be bounded here. After that, there were papers by Ivashov-Musatov, Körner, many people with very delicate estimates of this behavior, but for us it is enough, this guy. Convolution can be considered with more or less standard looking Young inequality, but of course, as always here with different norms. The parameters are the same, but the norms are different. And all these new notions, new tools, in our work, they started to have applications. There are two applications, meantime. One application is a version of an uncertainty principle. One of the classical notions of uncertainty principle, which is known as Amrain and Berthier result, it is used for this version of the uncertainty principle. And finally, the solution of that initial problem, which motivated us to work in this direction. Now we are again in the scope, in the one-dimensional setting, and we introduce these norms. This is an analog of those OP spaces, but for measures. And now we consider both the sine and cosine Fourier transform by applying this parameter gamma. And we have the following theorem. The functions of bounded variation vanishing in infinity, no word about absolute continuity. And we have this almost asymptotic formula. For the cosine transform, this does not appear. And for the sine transform, we have a really sort of the leading term and remainder term. And we follow one of the known proofs of direct proofs of what I showed in the beginning. We integrate by parts, we work. This guy is important. This guy is very important. For functions, it is a simple one-line long fact. But here it is a lemma, important lemma with some technical proof. And we do some standard calculations, and at certain moment we apply Hölder's inequality, and finally we arrive at the Fourier transform in this power, and we need an analog. Here we need an analog of the Hausdorff-Young inequality, and we do have it. We have obtained it above, and we apply, and by this we arrive at the needed result. Believe me, this can be done, and some result can be formulated and proved in many dimensions. My book, relatively recent book, which is titled Functions of Bounded Variations and their Fourier Transform, has two parts. One is multidimensional and all the things, but no need to have additional difficulties with these notations, technicalities, and all this stuff. What is really of importance, these results, they claim for new applications. This is only a starting point. One more thing, let me bring your attention to it. I'm not sure that this approach, this way of simulation is the only way, unique way. My feeling is that there might be more ways, maybe even more than two, and it would be really of great interest to find some other approaches and to compare them, whether they are equivalent or not, and maybe some approach will be more effective, I don't know. But new applications are really needed. Thank you for your attention.